Inclusion complexes are also called occlusion compounds, in which one of the components is trapped in the open lattice or cage-like crystal structure of the other. Here, the interaction is not due to chemical reactivity, but because of the favorable molecular architecture. The forces of interactions are weaker. It is difficult to predict the formation of inclusion compounds between two selected compounds. These complexes generally do not have any adhesive forces working between their molecules and are therefore also known as no bond complexes. An inclusion compound is a complex in which one chemical compound, which is called as a host, forms a cavity in which molecules of a second compound, which is the guest compound, are trapped. So, inclusion compounds are a class of addition compounds where one of the constituents of the complex is trapped in the other to yield a stable layout. So, this is a type of host-guest compound, and it depends on the architecture arrangement rather than chemical affinity. So, there are no adhesive bonds, neither there are other types of bonds, but it is only the host taking up the guest molecule in its cavity. Inclusion complexes are further classified as channel lattice types, clathrates, that is layer types, monomolecular inclusion complexes, and macromolecular inclusion complexes. So we'll first discuss now the channel or the lattice types of inclusion complexes. In this complex, the host component crystallizes to form channel-like structure into which the guest molecule can fit. The guest molecule must possess a geometry that can be easily fit into the channel-like structure. These channels are formed by crystallization of the host molecule, and the guest components are usually long, unbranched, straight chain compounds. Channel lattice types of complexes provide a means of separation of optical isomers. Example, DL-terpineol has been resolved by the use of digitonin. So, these channel lattice type of complexes are used for separation of optical isomers. The cholic acid, that is the bile acids, can form a group of complexes principally involving deoxycholic acid in combination with paraffins, organic acids, esters, ketones, and aromatic compounds, and also with solvents such as ether, alcohol, and dioxin. The crystals of deoxycholic acid are arranged to form a channel into which the complexing molecule can fit. The cholic acid, that is bile acids, can form a group of complexes principally involving deoxycholic acid in combination with paraffins, organic acids like acetic acid, salicylic acid, esters, ketones like menadione, and aromatic compounds, and also with solvents such as ether, alcohol, and dioxin. The crystals of deoxycholic acid are arranged to form a channel into which the complexing molecule can fit. The crystals of deoxycholic acid are arranged for forming a channel into which complexing molecule fits. The architectural arrangement of the complex is shown in the figure. There are other types of channel forming substances which are the host like urea, thiourea, amylose, etc. The guest agents can be paraffins, esters, acids, ethyl alcohol, dioxin, etc. The well-known starch iodine solution is a channel type of complex in which iodine molecules are trapped within the spirals of the glucose molecules. Urea can be used as a host which forms complexes with many compounds. Example, vitamin A palmitate can be complexed with urea. In this complex, the vitamin A palmitate oxidation is prevented. The other example where urea can be utilized to form complex is with vitamin E and also with famotidine. The dissolution of these two drugs can be improved by complexation with urea. Urea and thiourea also crystallize in a channel-like structure permitting enclosure of unbranched paraffin, alcohols, ketones, organic acids, and other compounds. Please understand that these molecules, which are the guest molecules, should be unbranched, straight chain compounds. They should be long, unbranched, straight chain compounds. Example, monostearine. Now, this monostearine acts as an interfering substance in the assay of dinesterol. And hence this can be extracted easily from dermatological creams by channel type inclusion with urea. Urea inclusion might become a general approach for separation of long chain compounds in assay method. Layer type of inclusion complexes. Compounds like clays and Montmorillonite, which is a constituent of bentonite, can entrap hydrocarbons, alcohols, and glycols. These form alternate monomolecular layers of guest and host. Their uses are currently quite limited. However, these may be useful for catalysis on account of a larger surface area. Graphite can also intercalate compounds between its layers. So you can see layer type of complex, which is also called as intercalation compound, is a type of inclusion compound in which the guest molecule is diffused between the layers of carbon atom to form alternate layers of guest and host molecules. Third type of inclusion complexes are the clathrates. Warfarin sodium is a clathrate of water and isopropyl alcohol. It is available as white crystalline powder. During crystallization, certain substances form a cage-like lattice in which the coordinating compound is trapped. For example, hydroquinone molecules crystallize in the cage-like structure with hydrogen bonding. The holes have a diameter of 4.2 angstrom and permit the entrapment of small molecules such as methyl alcohol, carbon dioxide, and hydrochloric acid. So these clathrates are basically compounds that crystallize in the form of a cage-like lattice in which coordinating compound is trapped. Chemical bonds are not involved in these complexes and only the molecular size of the encaged component is important. Clathrates can be used to separate optical isomers. Example of clathrate. Hydroquinone crystallizes in a cage-like hydrogen-bonded structure in which small molecules such as methyl alcohol, carbon dioxide, and hydrochloric acid may be trapped in these cages. Size of the guest molecule is important for complex formation. If the size is too small, the guest molecule will escape from the cage of the host, and if the size is too big, it will not fit inside the cage. Synthetic metal aluminosilicates are known to be used as molecular sieves. These materials are used to store gases, volatile and toxic substances by the mechanism of clathrates. The clathrated guest molecule can be later removed by simple physical process. Macromolecular inclusion complexes include substances such as zeolites, dextrin, and silica gel. These act as molecular sieves. The atoms are arranged in three dimensions to produce cage-like, that is clathrate-like, and channels in which the guest molecules are trapped. Synthetic zeolites can be made to a definite pore size to separate molecules of different dimensions. Monomolecular inclusion complexes. These involve the entrapment of a guest molecule in the cavity of one host molecule. Most of the host molecules are cyclodextrins. Cyclodextrins are cyclic oligosaccharides containing a minimum of 6D glucopyranose units attached by alpha-1,4 linkage. Three types of cyclodextrins, namely alpha, beta, and gamma, consist of 6, 7, and 8 units of glucose respectively. Cyclodextrin has the smallest cavity with internal diameter almost 5 angstrom. Beta and gamma cyclodextrin have larger internal diameter 6 and 8 angstrom respectively and are useful for pharmaceutical formulation. The structures of cyclodextrin assume a truncated cone and can accommodate a wide variety of compounds. The interior of the cavity is relatively hydrophobic, whereas the entrance of the cavity is hydrophilic in nature. Cyclodextrins involve the entrapment of a single guest molecule in the cavity of one host molecule. They can form water-soluble inclusion complexes with small molecules or portions of large molecules. Interior is relatively hydrophobic because of the CH2 groups, and the exterior is hydrophilic because of the OH groups. Cyclodextrins are produced by a simple procedure from starch by means of enzymatic conversion. The inner cavities are able to interact with hydrophobic molecules and thereby increase their solubility. Cyclodextrins have truncated cone structure with a hydrophobic interior cavity because of the CH2 groups and a hydrophilic exterior due to the presence of hydroxyl groups. Molecules of appropriate size and stereochemistry get entrapped in the cyclodextrin cavity by hydrophobic interaction, thereby squeezing out water from the cavity. The beta and the gamma type of cyclodextrins are the most useful for pharmaceutical technology owing to their larger cavity. Cyclodextrins can enhance the solubility and bioavailability of hydrophobic compounds due to the large number of hydroxyl groups on the cyclodextrins. Although beta-cyclodextrin contains a higher number of hydroxyl groups, beta-cyclodextrin solubility is the lowest compared to alpha and gamma-cyclodextrin. This is due to the formation of internal hydrogen bond network between the secondary hydroxyl groups. Beta-cyclodextrin has a limitation that it cannot be used in parenteral formulation because of its low aqueous solubility and nephrotoxicity. Partial alkylation of some of the OH groups in cyclodextrin reduces the intermolecular hydrogen bonding, leaving some hydroxyl groups free to interact with water, thus increasing the aqueous solubility of cyclodextrin. In addition to hydrophilic derivatives, hydrophobic forms of beta-cyclodextrin have been used as sustained release drug carriers. Hydroxypropyl beta-cyclodextrin shows improved solubility as compared to beta-cyclodextrin. In addition to improving the solubility of compounds, complexation with cyclodextrin has been used to improve the stability of many drugs by inclusion of the compound and protecting certain functional groups from degradation. Example, the stability of drugs such as aspirin, benzocaine, ephedrine, and testosterone is improved when complexed with beta-cyclodextrin. The inclusion complexes protects the drug by preventing the exposure of the functional groups to the exterior of the environment. Complexation with cyclodextrin has also been used to mask the bitter taste of certain drugs like femoxytine. Compounds having very high affinity towards the cyclodextrin cavity will dissociate at a very slow rate from the complex, and these inclusion complexes will thus exhibit sustained release of the drug or the active. Hydrophobic cyclodextrin derivatives have been used as sustained release drug carriers. Ethylated beta-cyclodextrin has been used to reduce the release rate of the water-soluble drug diltiazem and isosorbide dinitrate. Liquid compounds such as plant essential oils and botanical extracts can be turned into powders and volatility is strongly reduced. This can be done with the help of cyclodextrin complexation. Pharmaceutical products that act via the transdermal route can have cyclodextrins in their composition, with an aim to improve the release and/or penetration across the skin, to improve the stability as well as to reduce the local irritation. Molecules that are sensitive to UV and visible radiation are protected by inclusion, since cyclodextrins can themselves act as filters against radiation and avoid photodegradation of the guest. For this reason, cyclodextrins are often employed in sunscreen compositions to protect the active ingredients. Included guest molecules are protected from the attacks of several reactive substances, and in this way the hydrolysis, oxidation, racemization, isomerization, polymerization and enzymatic decomposition reactions are eliminated or minimized, which results in extended shelf life of the products containing inclusion complexes with cyclodextrin. Example: stability of aspirin, benzocaine, ephedrine, and testosterone is improved when complexed with beta-cyclodextrin. So in short, we can say that cyclodextrins have variety of applications. That is, they can be used to increase the solubility. Example: the solubility of retinoic acid, which is 0.5 mg per liter, is increased to 160 mg per liter by complexation with beta-cyclodextrin. It can enhance stability, as discussed, by preventing the exposure of the functional groups to the exterior environment. Example: it can be used to stabilize drugs like aspirin, benzocaine, ephedrine, and testosterone. Then it can be used to mask the bitter taste of the drug and also to mask the odor of the drug. It can be used to increase the dissolution rate of drugs such as famotidine and tolbutamide by complexation with beta-cyclodextrin. It can reduce the volatility of certain compounds by entrapping these compounds in the cavity of cyclodextrin. It can be used to reduce the incompatibility between the drug and the excipients. It can be used for sustained release. Example: ethylated beta-cyclodextrin retards the release of drugs such as diltiazem and isosorbide dinitrate when complexed. The drug releases slowly for prolonged periods and provides a sustained release effect.